Welcome to section 4 of chapter 2, acceleration. Okay, what is acceleration? Acceleration is a new concept that we define as the rate of change of velocity. Velocity can change by a certain amount in some time interval, and we define acceleration as how much the velocity changes in some time interval. So we can rewrite this expression as the change in velocity is, as always, our final velocity minus our, in our x direction, the initial velocity divided by some time interval. This is also the slope of a velocity versus time graph, as we will see shortly. Let's take a case example of two cars, the Chevy Corvette and the Chevy Sonic. The Corvette can go from 0 to 60 miles per hour in 3.6 seconds, while the Sonic takes 9 seconds to accelerate to the same final speed. In our SI units, the velocity 60 miles per hour converts to 27 meters per second. I'll let you do that on your own. Therefore, the Corvette speeds up to 27 meters per second in a time interval of 3.6 seconds. Let's find the acceleration of the Corvette. It's equal to the change in velocity divided by some time interval. In this case, 27 meters per second divided by 3.6 seconds. If you put that into your calculator, you get 7.5 meters per second divided by seconds. Once again, what do these units mean? Well, that is simply 7.5, that's a point here, decimal, meters per second, or meters per second squared. We say meters per second squared. That's the acceleration of the Corvette. Just to follow up with the Sonic has an acceleration. Again, we're using the same expression, how much the velocity changes in some time interval. In this case, we have the same final velocity, same initial velocity, but a time interval of 9 seconds. That gives me 3 meters per second squared for the Sonic. Okay. If we were to graph this on a velocity versus time graph, we see the Corvette achieves a faster velocity in a shorter amount of time. So for every second, the velocity increases by 7.5 meters per second. And we see that the Corvette has a steeper slope relative to the Sonic. We could put this into tabular form, but more importantly, we'd like to look at it as a graph. So we can say that the object's acceleration is the slope of the velocity versus time graph. We've seen something like this before. However, then we said that an object's velocity is the slope of the position versus time graph. Sorry that that's so small. So we can find the acceleration graph from a velocity graph similarly to how we found velocity graphs from our position graphs. In this case, what we have in this first unit of time, we see that the velocity increases linearly, which means we have a constant slope. Constant slope in velocity means a constant acceleration. Remember, the slope of the velocity graph is the acceleration. So we have a positive constant velocity. We have a positive acceleration. We're above the origin, positive value for acceleration, and it's constant. In the next portion of time, our velocity is unchanging. What is the acceleration when our velocity doesn't change? The acceleration must be 0. Constant velocity means 0 acceleration. Here we see 0 acceleration. Then our velocity decreases. It goes back to 0. We have a negative slope here. That corresponds to a negative acceleration. And we're going to discuss more what the meaning of negative acceleration means because it is a little bit ambiguous. Let's do an example. Lions, like most predators, are capable of very rapid starts. From rest, a lion can sustain an acceleration of 9.5 meters per second for up to 1 second. How much time does it take the lion to go from rest to a typical recreational runner's top speed of 10 miles per hour? Well, we're given a lot of information here. So let's take a look and break it down little by little. Okay, so the first piece of information we have is that the lion can sustain an acceleration of 9.5 meters per second squared. So I'm going to make a little table of my known values. The acceleration of the lion is 9.5 decimal meters per second squared for up to 1 second. How much time does it take? So the question is asking for some time interval for a lion to go from rest, that means my initial velocity in the x direction, and this should be an x here, initial is equal to 0, right? Rest means 0, to the recreational runner's top speed of 10 miles per hour. So Vx final is 10 miles per hour. Now I need to convert that into our SI units. So V final, Vx final is equal to 10 miles per hour, and I can look up, or maybe I remember the conversion. There are 0.45 meters per second in 1 mile per hour. So 0.45 times 10 is 4.5. Miles per hour cancel, and I'm left with meters per second. Okay. So I can then write here my final velocity is 4.5 meters per second. Now, what am I asked to find? I'm asked to find how long does it take the lion to achieve that final speed. Well, if I remember from my definition of acceleration, it's equal to the change in velocity in some time interval. So if I solve this for time, multiply both sides by delta t, cancels on the right hand side, and then divide both sides by acceleration. And I see that delta t, cleaning this up a little bit, is equal to the change in velocity divided by the acceleration. So my change in velocity is 4.5 meters per second minus 0, final minus initial, divided by the acceleration, which is 9.5 meters per second squared. Now the meters cancel all over the place. Actually, I can just ignore this term because it's 0. Meters cancel. I have 1 over seconds on top and 1 over seconds squared on the bottom. So one of those meters on the bottom cancels with the 1 on top, and the seconds in the denominator of the denominator moves to the numerator. So my units work out so that time is measured in seconds. 4.5 divided by 9.5 is 0.47. It took less than half a second for our lion to reach top speed, or actually not his own top speed, but a runner's top speed. That's a little intimidating. I hope to not meet a lion in the wilderness. So let's go back to the sign of the acceleration. Now we know that objects can move right or left or up or down while either speeding up or slowing down. Now, we colloquially we often say that an object decelerates when it slows down and accelerates when it speeds up. In physics, however, we never use the term decelerate. We always talk about acceleration, which can be either positive or negative. Now, for an object, in this first case, that is moving to the right and speeding up, we see the motion diagram shows the velocity vectors increasing in length and pointing to the right. The acceleration vector we can draw along with our motion diagram as an arrow that points from the shorter arrows to the longer arrows, so from small velocities to larger velocities. That's how we define the direction of acceleration. The acceleration in this case is positive. If we were to graph this, we see that the velocity is positive because my object is moving to the right. So the velocity is in the positive quadrant. It also has a positive slope given by the acceleration to the right. We have another situation that looks very similar. In this case, our object is moving to the left and slowing down. Notice then that the longer arrows are still on the right and they get shorter and shorter as you move to the left. So the acceleration vector points to the right because the rightmost velocity vector is longer than the leftmost velocity vector. So this object is also has positive acceleration. What does that mean graphically? Well, our velocity is negative because we're moving to the left. That means the velocity is in the bottom quadrant. However, the acceleration is positive, so we have a positive slope. The velocity is getting closer and closer to zero. The object is slowing down, but we're moving in the negative direction. This is going to take some practice to get your head around the meaning. There's a lot of meaning in these velocity graphs. There's a lot of information that we can pull from them. So practice, practice, practice. Let's take two more situations. Here, we now have an object that is moving to the right in the positive direction. However, it is slowing down. Therefore, the velocity is positive because the object is moving to the right. However, that velocity is getting closer and closer to zero. We have a negative slope. That negative slope means our acceleration points to the left. On our motion diagram, we can also say that the acceleration vector points from the small arrows to the larger arrows, so it points to the left. We have another similar situation. However, in this case, our object is moving in the negative direction and speeding up. The object is moving in the negative direction, which means the velocity graph is in the negative quadrant, the lower quadrant. And because it's speeding up, the acceleration vector is going to point from smaller vectors to larger vectors, in this case, to the left, indicating a negative slope. Negative acceleration, negative slope. Velocity vectors are getting longer as you go to the left. Negative acceleration, negative slope. So in these two cases, you can see all we've done is we've shifted our velocity from the upper quadrant, from the positive, to the lower negative quadrant. In the first case, we have an object that is moving to the right and slowing down, has negative acceleration, or moving to the left and speeding up, negative acceleration. Again, keep practicing problems like this to get your head around the difference between positive acceleration and negative acceleration. Okay, thank you.